share. Okay. Okay. Uh, so if there is any quick question regarding earlier lectures, I can answer that. Otherwise, I'll start from here. So last day what we have done actually, we have discussed the Noether's theorem, which basically tells us that. Let me go there and then just I'll recapitulate a few things and then quickly go to the today's lecture, because this is a very important theorem, which is extremely important both for classical and quantum physics. So Noether theorem tells us that if the action S, which is normally written at the integral or time integral over the Lagrangian density, if the action remains invariant under certain transformation, then corresponding to that transformation there will be some conserved quantity. And that we have shown you explicitly, that suppose you have a system which is invariant under rotation, then the conserved quantity will be the angular momentum, right? This I have shown you because I have calculated change the x to x plus delta x, and then also calculated the change in action, and this delta x, when I specify that delta x for the rotation, then I have shown there, then the angular momentum will be a conserved quantity. Like this kind of two-dimensional rotations I have taken and shown you that angular momentum will be a conserved quantity. Now, if you take that delta x, x is equal to x plus some, say, let us say a, that means if I just make a translation, you can easily show that the conserved quantity will be linear momentum, right? And if you take that, if you translate it in time, then you will see the Hamiltonian will be, or the total energy will be conserved. Then that I have generalized to classical field theory. What we have done there, that in the classical field theory we have a function phi which depends on both time and coordinate. I made a change in the coordinate system. X mu is a 4 vector. This is a quantavariant vector. I'll come back. If I'll explain that either today or maybe tomorrow in details, what is a quantavariant and covariant vector and what is the difference between them. So suppose I make a change in the this x mu is 0, 1, 2, 3. So mu equal to 0 is the time, and mu is equal to 1, 2, 3 is the space coordinate. So suppose when we have a classical field phi, which is a function of x, then that phi can change if I change x, right? Also, the phi can also change if I just make a phase transformation like this. So both way phi can change, and now the total change in phi will come from the change in x and also change in phi. So because of the change in phi, I can now calculate the change in the Lagrangian, and change of the Lagrangian will give me a change in the action. And all these steps I have done in detail and shown you the change in the action will be something like this, So you see it is delta S equal to d4x times 4 divergence, because mu is 0, 1, 2, 3 times this particular quantity. Now you see if delta S is equal to 0, the change in the action is 0, then you see there is a quantity here del mu times something. Del mu, this is a current kind of thing. Del mu, J mu will be 0. So that J mu will be the conserved current. So that conserved current will depend on what kind of conserved current we are talking about, will depend what is the change you are making in the coordinate x and what is the change we are making in the delta phi. Then I gave you an example there, that suppose I change the let me go there. I change only the x coordinate, 4 coordinate, del x mu equal to epsilon mu, and no change in phi, right? Then what I have seen there, that the conserved current from there I have calculated, which is theta mu nu. And theta mu nu, actually I'll show you, this will turn out to be the energy momentum tensor. And then the 0th, if the J mu nu 0 equal to theta mu nu, this is the the energy momentum tensor. And when from our experience in classical electrodynamics, then we write the conservation equation as del mu J mu equal to 0, where J mu is the electric current. And their J mu is a 4 vector. The temporal component is the charge density, and the spatial component is the current density, right? Now, if and the temporal component is mu equal to 0 component of J mu. Similarly, if I take the 0 mu equal to 0 component, that will give me the energy momentum. Okay, so Noether's theorem tells me that if I make a change in the coordinate system like this, then all these steps, if you follow, it will tell you that this quantity will be conserved, right? Now, suppose I take nu equal to also 0, and with nu equal to 0, I evaluate this theta mu 0. I'll see that what I am getting is phi dot minus L. And please recall that this is with your classical mechanical experience, that H is P Q dot minus L, that is the Hamiltonian. So this is the Lagrangian. This is phi dot is equivalent to Q dot, which is the dynamical variable in classical field theory, and P dot is pi, because pi I have defined as del L del L del phi dot, like P is del L del Q dot. So this is nothing but the Hamiltonian, and when I integrate over this d cube x, that is the total energy. So total energy will be conserved, right? If my, and I have chosen mu equal to 0, that means when I have taken mu equal to 0, that means I have given a translation in time only. And that means if the system is invariant under time translation, then total energy will be conserved. That is what we have discussed. Now let us get back to today's discussion and start with the theta mu nu, the energy momentum tensor, which we have described, defined on the other day. Now, the conservation of energy and momentum will hold when this L is independent of x mu. X mu is it is independent of the x vector and time. This will of course hold because if you have an isolated system, then the isolated system today and tomorrow will not change. So that will certainly remain unchanged under time translation. And isolated system, if you take isolated system from here to Bombay, nothing will change. That means if I give a translation, then nothing will change. So that is the statement of the Noether's theorem, which we have proved for mu equal to 0. That means for the time translation, right? That total energy is constant. So for such a system, you know, this theta mu nu is this, right? Now we have also, you know, derived the Lagrangian density for the scalar field, right? How we have derived this? What we have done, we said that suppose I have a scalar field phi, right? And from that scalar field phi, I want to derive an expression for Lagrangian, which will be invariant under Lorentz transformation, condition number 1. And the equation of motion which I will get from this L should be linear. Then I have argued that this will have only del mu phi, mu covariant and contravariant, and whenever there will be mu totally contract up down contracted, that quantity will be called Lorentz scalar, and that quantity will always be invariant, and this is also an invariant quantity. So this L we have constructed, and if I put the L here, what I get theta mu nu equal to this. And this theta mu nu, if I raise the index nu there, then this becomes theta mu nu. Please note here that this is, if I change mu to nu, this is symmetric. This theta mu nu, the energy momentum tensor, is invariant under the interchange of mu and nu. That means theta mu nu is equal to theta nu mu. However, this is always not true. There will be situations where this energy momentum tensor can be asymmetric also. In that case, we can make it symmetric by adding certain terms. This is just this is slightly away from our course, but there are some questions, so that is why I'm discussing this. The theta mu nu, I can change to theta mu nu plus some other function, add some other function f mu nu, which also depends on t and x. When I write small x, this contains both the x vector as well as the time, right? If I can add a term always to make it a symmetric, provided that extra function f mu nu satisfy this 4 divergence, right? Also, that will, this f mu nu, if I put mu equal to 0, again that is something like a charge, the integration of that should be equal to 0. If this f mu nu function satisfy this condition and this condition, then one can show the solution that function like f mu nu, derivative with respect to lambda, f mu nu lambda. This function, if I add this kind of f mu nu, which will satisfy this del lambda f mu nu lambda, which will come as a solution like this. If I add there, then my Lagrangian will be energy momentum tensor will be symmetric. Now this is just a passing comments I am making. All the steps are done. You can check, and then you may ask thus why this energy momentum tensor needs to be symmetric. All you know that in general relativity, the equation of motion is the famous Einstein equation, which is, I will not go into this detail. R mu nu is the Ricci tensor, all right, and half R is the trace of the Ricci tensor, and this G mu nu is the metric tensor. So this is the left hand side which involves the space-time curvature, and then that is equal to 8 pi g theta mu nu. Now this Ricci tensor and G mu nu, the metric tensor, both are symmetric. And then in the Einstein equation, left hand side you have the metric tensor, the space-time tensor, and right hand side you have the energy momentum tensor. So if the left hand side is symmetric, then right hand side has to be symmetric. That's why you need to construct energy momentum tensor which should be always symmetric. That is to say that energy momentum tensor here acts as a source for the gravity, or this source for the space-time curvature. And since this part is symmetric, then theta mu nu has to be symmetric. That's why if you can always construct a symmetric energy momentum tensor. Now this is the requirement to make this is symmetric. Now I'll go back to the Klein-Gordon equation again. Okay. In the Klein-Gordon equation, I have written down the Klein-Gordon equation for a scalar field, half del mu phi minus m square by 2 into phi square. Now suppose I have two fields, phi 1 and phi 2. Then the Lagrangian will be del mu phi 1, one part for the phi 1 and the other part for the phi 2. Now this, what I can do, I can define a field capital phi as a combination of phi 1 plus I phi 2, a complex phi and its complex conjugate. So from phi 1, phi 2, 2 degrees of freedom, I am going to phi and phi star, other 2 degrees of freedom, other two field variables. From two field variables phi 1, phi 2 to I am going phi and phi star, right? And then if I put phi 1 and phi 2 in terms of phi and phi star in this Lagrangian, I'll get the L Lagrangian is del mu phi star minus m square phi star. Okay, this is my Lagrangian for the complex field. This will be clear why I am discussing complex fields, because if you have charged particle, then any charged particle will have a antiparticle, right? So if you have an antiparticle, particle and antiparticle, then for a charge system like this is not such will be valid for the electron and positron, because electron and positron, they are Dirac field, they are fermions, but we are now discussing scalar, right? So like in the particle world, it could be pi meson, pi plus and pi minus, so to say, right? Or in case of charge Higgs, this will be also valid. So the Lagrangian density del mu phi star minus m square phi star. I need 2 degrees of freedom if I want to discuss the charged particle. So that is why I have considered here the charged complex field. But it is easy to show that if I add these two Lagrangian for the two real field phi 1 and phi 2, I can construct through this transformation. I can get a Lagrangian for the complex field. Now suppose I give a transformation to this phi e to the minus I alpha phi, and phi star will be then e to the plus I alpha phi star. This is just a transformation I am giving. Now suppose alpha is very small, then I expand this exponential and keep the first term, and phi star, also I keep the this term. Then change in phi will be just phi prime minus phi is minus I alpha phi, and change in phi star will be I alpha phi star. Why I am making this change? Because I have shown you that the total energy is conserved in through this Noether's theorem if I give a translation along time, right? And I said that the change in phi can come from either from x or from directly from phi. So I am now discussing if the phi is changed, then what is the conserved quantity, right? So that is the motivation for doing this. So I have changed the phi through this phase transformation, where alpha is just a constant. If alpha is a constant, then that transformation is called a global transformation. If alpha is not a constant, if it is a function of t and x, then you will see later very interesting physics. The kind of Lagrangian you will get for such things, will be for complex field. I will have probably the chance to discuss that. Then the Lagrangian which you will get, that kind of Lagrangian you can use to understand the Higgs mechanism. That you can also similar kind of Lagrangian you can use to understand the Landau-Ginzburg phase transitions. You can use that kind of Lagrangian to understand the Meissner effect in superconductivity. So that I will discuss later. But complex scalar field is very interesting. Will give some interesting physics. Now what I am doing there, I have made a change in the phi through this phase transformation, and then for that change in phi, what is the current that I want to calculate? This current, please see that this I have already calculated for you in the last day. So this, this J mu I have calculated, and then I want to see what is this J mu, this current for this kind of phase transformation in phi. And here what I am doing, I am not changing x. The argument of the variable phi, classical field phi, I am not changing. So this is the pure change in the phase. So when I put that pure change in the current, you'll be surprised to see that current will be just I phi star del mu phi minus phi del mu phi star. And this is the current, if you remember, in your relativistic quantum mechanics, you got it from Klein-Gordon equation. And that Klein-Gordon equation, this is the current. And this mu equal to 0 component will be the probability density. Now, that probability density, which is the mu equal to 0 component, is this. Now, you know that this is the current density, right? Now, if I multiply this by the electric charge, if I say that phi is carrying some electric charge, then this J0 multiplied by E will be nothing but the electric charge density, right? And if I integrate that electric charge density over volume, then I get the total charge. And if total charge is the total charge, now we take the time derivative of this total charge, and and then just take it and you will see the total charge is conserved. That means what I have done here, I have changed the phi to a global phase transformation. Global I am saying because alpha is independent of t and x. That I have taken. I have found out the Noether currents. From the Noether currents, I took the 0th component, which is the charge density. I integrate that charge density over the volume, so I get the total charge, and its time derivative is 0. So the total charge is conserved. That tells me that if my action or the Lagrangian is invariant under global gauge transformation, right, global phase transformation, then total charge of the system will be conserved. That is the consequence of the theorem of Noether's theorem. Okay. Now let us go back to quantization of the field. Okay, which is our main purpose. Let us get back again to the real Lagrangian for the real scalar field. This is the Lagrangian, and I have derived this equation, Euler-Lagrange equations for you. How? Because I wrote down the action for this Lagrangian, S equal to L d4x. Why d4x? L dt was the action, but it is Lagrangian density, so there is a d cube x. So d cube x into dt is the action S. So what I have done there in this S, I have taken the set that I want to find a equation of. We did that and got this equation of motion, right? And this is the equation of motion we have got. Just a passing comment, which is very important. We are using the natural unit where h bar is equal to 1. So if h bar equal to 1, I am measuring action in the unit of h bar. So this action is dimensionless. Actually, in ordinary quantum mechanics, it will always come as s by h bar. But h bar I have taken equal to 1. I am measuring everything in the unit of h bar. So this s is unitless. L d4x must also be unitless. d4x has a dimension of length to the 4. So L, the Lagrangian density, should have a dimension of L to the minus 4. And in the first day, I have shown you that in this natural unit, the length and mass, they are inversely proportional. Then if L has a dimension L to the minus 4, then this L should have a dimension of mass to the plus 4. This is very important because in 4th dimension, the Lagrangian should have this kind of dimension, and when we will introduce the interaction, we should be careful that when I am introducing any interaction in the Lagrangian, you should have a proper dimension. If you don't have, if you have higher dimension or lower dimension, that will affect the renormalization procedures of the field theory. That is a advanced topic. If opportunity comes, we'll discuss that. Now, how we got this equation of motion? We got the equation of motion, say point 1 to point 2 when the particle is moving. We have found out that along which path this action is optimum, and that gave me the classical path. Okay, and that gave me the equation of motion for the classical field. Right, and in this lecture, first I will discuss the canonical quantizations. There is another alternative to discuss the quantum field theory, is the path integral approach, which, if time permits, and I will be happy to discuss later. Okay. Now, but basically, what in path integral one does is that, suppose you take an analogy of a young double slit experiment, that you have a source here, and then you are observing something here, and you have this wave can go through the 2 holes in this screen, A1 and A2. Then when you calculate the amplitude, you take the sum of these 2 paths. It goes from S to A1 to O, and plus S through A2 to O. And if you have many holes, then you should take S going to other hole A3 to observable point O, and so on and so forth. Now, suppose you add up all the amplitudes. And in quantum mechanics, you know there is no well-defined trajectory. So particle can go from this to this through any point, right? And that will be equivalent to saying that between this S and O, you have infinite number of screen with infinite number of holes. That will tell you that you have to take this sum over all these space-time points. And when you do that sum you perform, that is actually equivalently you are taking integration for all the paths. And that is the path integral formalism proposed by Feynman. That we'll discuss later. But this approach we are not going to discuss. We are going to discuss here canonical quantization. Why I am doing that? Because we are use this similar kind of quantizations in our non-relativistic quantum mechanics. So this will give a better understanding of the physics. And then, if time permits, this is a very powerful technique, path integral formalism. We'll discuss later. Okay. So back to the canonical quantization. So this is my Lagrangian. This is my Lagrangian. I can this del mu phi. I said this mu contains mu equal to 0, 1, 2, 3, and mu equal to 0 is the time component. So this I can write as the time component, and this all the space component as a gradient. So mu equal to 0 is del 0 phi, and this is del phi del x, del phi del y, del phi del z, which is combinedly written as gradient of phi square minus m square phi square. Now I take the derivative of this L with respect to phi dot, like you take the derivative of L with respect to Q dot, because Q was your dynamical variable in classical mechanics. Here, classical field theory, phi is my dynamical variable. So I'll take the derivative of L with respect to the phi dot, like you did for Q dot, right? Then pi del L del phi dot, if you take the derivative, then you see that this pi will be equal to phi dot, simply. Pi will be equal to phi dot, right? So if pi equal to phi dot, then I can calculate the H again, minus L plus pi phi dot. In classical mechanics, minus L plus P Q dot. Simply that P and Q are the dynamical variable. Here pi and phi are the dynamical variable. P and Q are conjugate. Here pi and phi will be the conjugate variables. So this H, I can put the L calculated from there in this particular expression, and then I get H as this. And I replace everywhere phi dot by pi, and I get the Hamiltonian for the system as a function of pi and phi, right? Like you write down the classical Hamiltonian in terms of momentum P and Q, never in terms of Q and Q dot. You always write the Lagrangian as a function of Q and Q dot, the dynamical variable Q and its derivative. But when you write down the Hamiltonian, you always write it in P and Q, right? Momentum and the coordinate Q. So similar thing has to be done here. This is the Hamiltonian. We'll be using this expression. Now we are going towards the quantization of the field. Now recall the transition, what you did when you have gone from the classical mechanics to quantum mechanics. What you did, you classical dynamical variables like Q and P, you have promoted them to operator Q and P. Dynamical variables are promoted to Q and P. And time was there just a parameter, okay? Now this Q and P, you have used the quantization relation, Qi Pj dot is equal to I Kronecker delta. Qi Qj you took 0, Pi Pj is equal to 0. I should have put here H bar, H bar delta Ij, but H bar I am taking equal to 1. Now if Q and pi is I delta Ij, remember I and J are discrete variables. Now for a continuous system, because classical field theory is a continuous system, I have shown you that how one can make a transition from a discrete to a continuous system by giving the example of that string. Now in classical field theory, as I said, my dynamical variable is phi. Like in the string, the eta was the dynamical variable. So phi is a dynamical variable, and its conjugate momentum, I have just calculated that pi is the conjugate momentum, del L del phi dot, like pi is del L del Q dot. So this Q is just phi, corresponding analogous dynamical variable. P, analogous variable, is pi, and then I, similar I, and this was a discrete variable, that's why it's Ij. For continuous x and y, I should just use, in place of Kronecker delta, use a Dirac delta function. So that's the quantization of the field, classical fields I am using here, right? And as I said, the dynamical Q and Q, Qi Qj is 0, phi x phi y must be 0, like Pi P is a 0, pi x pi y commutator should also be 0. So this commutator pi x pi y is equal to I into Dirac delta function with argument x minus y. This is the quantization conditions for the field, which I have just used the analogy which you did in classical mechanics. And this quantization condition has been done for time t equal to 0. T equal to non-zero value I will introduce little later. But this is the for equal time quantization, you will see it will remain, this quantization will remain the same. And you know, this is extremely important to understand that this the consequence of the putting this commutator equal to I delta 3x minus y. You know, other day in the first lecture I have said that you know, when I calculate the amplitude of a particle propagating from a point x naught to another point x, I have shown you that propagating amplitude is becoming non-zero if at all space-time point. That is not allowed, because we are the light, you know, in special relativity tells you that you cannot have propagation of the particle outside the light cone. But when you say that some amplitude is non-zero for any ta and x, then you are violating the special theory of relativity. We'll see that these quantization conditions will restore that, you know, will restore the violation of causality what will happen is that, the propagation amplitude of a particle outside the light cone will be cancelled by its antiparticle. And that's how, the causality will be restored and your theory will be consistent with the quantum mechanics. Special relativity and quantum mechanics will be consistently built. Okay, so this is the quantization condition. Okay, just the analogy, please look into this. Now again, the Klein-Gordon equation I can write like this. Del mu, this I have already derived, and this time component is like this, and phase component minus gradient square plus m square phi equal to 0. Now what I am going to do is that I am going to take the Fourier transform of this equation with respect to only x. So what is that? Phi will be a function of x and t. I take d cube p by 2 pi cube e to the I p dot x. Phi tilde, which is the Fourier transform of phi, which is a function of p and t. Now, if time component is there, I have taken the Fourier transform with respect to x only. Now just recall, suppose I have a Fourier transform gp of a function of f of x, right? Suppose it is a Fourier transform of f of x. Then you can ask a question, what is the Fourier transform of df dx? You can see very easily, it will be just ip times, ip is coming from here, times the gp. So if I take if I know the Fourier transform of a function, and if I multiply that by ip, I'll get a Fourier transform for its derivative. Why I am doing this? Because I have a double derivative here. So I know the Fourier transform of phi, right? If I want to calculate the Fourier transform of the double derivative, I'll just multiply that by ip square. If you do that, the Fourier transform of that equation will be del square del t square plus p square coming from this, ip twice, p square plus m square operating on phi tilde pt equal to 0. Now, I define a variable omega p square equal to p square plus m square. Then my equation is del square del t square plus omega p square operating on phi tilde equal to 0. This is a wonderful equation. Please recall your harmonic oscillator equation, del square x del t square plus omega square x equal to 0, where omega square was k by m, right? Where k was the spring constant and m was the mass of the particle, right? So this is exactly very analogous to by taking the Fourier transform of the Klein-Gordon equation for the variable p. What I got an equation which is looking like a harmonic oscillator equation. Now, harmonic oscillator you have studied in classical mechanics, right? And then you know how to quantize it, right? So you are very close to the point which we are going to discuss. So you see, now one difference, of course. Here you had a spring constant k divided by m, that was our omega square. So you had a single spring constant, right? Single omega. But here what you have got, this harmonic oscillator equation is del square del t square plus omega p square is this. Now the omega p is root over p square plus m square, and that root over p square and m square, that p can take a value from 0 to infinity. Just please try to understand this, that you have a value p equal to 0 to infinity. So as if you have a set of harmonic oscillator with infinite number of spring constant, right? So this is just 1 minute, please. So sorry. So this p, you see, here you have a single spring constant. Here you have infinite set of harmonic oscillator with infinite number of spring constant, because this p momentum can go from 0 to infinity. Sure, I mean p can take any value from 0 to infinity. So you have an infinite number of harmonic oscillator here, right? Now, what you have done for a single harmonic oscillator, you just do that for infinite number of oscillator, right? Then you reach the quantizations and you use that same techniques and all that, right? Because P, the momentum P can take a value from 0 to infinity. So my frequency can be, so I have infinite number of oscillators with frequency given by omega P, and that infinite number corresponds to P equal to 0 to infinity. So what I did for single harmonic oscillator, I am going to do that for the infinite number of oscillator. That sets the base for the rest of the physics. Okay. Now just let me recapitulate what we did for harmonic oscillator then, right? Harmonic oscillator Hamiltonian was P square by 2m plus half omega square x square. So this was my Hamiltonian. Now let me take for convenience m equal to 1. Mass is unity. Just for convenience, you don't have to take it if you don't want. Then the Hamiltonian P square by 2 plus half omega square x square. This is my harmonic oscillator. Why I'm doing this? Because my Klein-Gordon equation has, somewhat boils down to an infinite number of oscillator problem. So now, then you remember you define a variable x in terms of the annihilation and creation operator, and the momentum in terms of the, again, annihilation and creation operator. And then you can invert this relation x and p to, in this particular fashion, A will be p minus I omega x, and A dagger will be, this is the annihilation operator and this is the creation operator, minus I by 2 omega p plus I omega x. Then the quantization relation, what you had is xp equal to I, right? I h bar, but that I am putting is equal to 1. So if I put x and p from this two particular expression x and p here, right? And then that will give me the commutation relations for A and A dagger. And if for A and A dagger, the commutation relations we will get equal to 1, right? If I take A dagger equal to 1, then my xp will satisfy the fundamental commutation relations. Xp is equal to I into H bar, right? This is what. Now, you see, in this particular case, my x, the dynamical variable, is phi, and in pi, which is, over p, the momentum, my conjugate variable will be pi, which is I have got from the Lagrangian by taking the derivative with respect to phi dot, right? Now, so I got the commutation relations. This part we have done. Just I'll give you a, discuss something interesting here, which I will be using later. Consider the Hamiltonian H equal to P square by 2 plus half omega square x square. I can write that as half P plus I omega x into P minus I omega x, right? Absolutely, there is no problem in that. I am in classical domain. So far I am in classical domain. You see, I have not put the hat. So I am in classical domain. And at this particular, after writing this in this particular fashion, I now make a transition to the, I promote these variables, dynamical variables, to the operator, as operator. Then H hat will be P plus I omega x hat, P minus I omega x hat. And if I put the, this in terms of the A and A dagger, you will get H hat equal to omega A dagger A, right? Now the question is, where is the 0 point energy? You usually get H dagger is equal to omega A dagger A plus omega by 2, right? Where is that, right? This is gone because I have written it in a certain order, which is called normal order, and that normal ordering will be using in the quantum field theory again. So you see, this is something very, very, very interesting, that how you make the transition, that up to this you write, and then make the transition, promote the dynamical variables to operator. You will not get the 0 point energy. Okay, that is one point. Now, so we have discussed so far this, x as 1 by 2 omega A plus A dagger, right? For a single harmonic oscillator. Now, I have infinite number of harmonic oscillator because of this omega p can take values from 0 to infinity, corresponding to p 0 to infinity. Now I'll use the same analogy. Phi x, which is the analogous to x, because x is the dynamical variable. Here pi x is the dynamical variable. Now 1 by root 2 omega, I had that, you see, 1 by root 2 omega, and then AP, the annihilation operator, right, plus the creation operator. But then I am writing that as a function of x, so I have to take the Fourier transform of these two quantities, integrate over dqp to get the phi x. So you see exactly what we have done there. I have written that a plus a dagger. This is simply phi, which is the dynamical variable a plus a dagger, and since I have infinite number of them from 0 to infinity, suddenly I have to integrate over them. That from p 0 to infinity I have to integrate. Similarly, pi, which is pi dot, you see what was our p here? P was minus I omega by 2. So remember that I will put minus I omega by 2, and since I have infinite number of them, certainly I have to integrate, I have to sum. See, here I have infinite number of harmonic oscillator, so I have to sum all the harmonic oscillator, and since p is a continuous variable, I have, instead of sum, I am doing the integration. That's it. So pi is again AP minus AP dagger. You see here there is a minus here, same I have put there, the minus I have put there. So this is my pi and pi, right? This is my pi and pi, like you have x and p, which you have written in terms of annihilation and creation operator. The x and p are dynamical variables. The phi and pi is my dynamical variable in classical in quantum field theory. So I have written them in terms of annihilation and creation operators in this particular fashion. Now I'll do a little bit simplification. This phi x has two terms, right? One with the associated with the annihilation operator, then the other with the creation operator. I have missed a dagger here. Okay, anyway, so I'll correct it. So this pi is this particular expression. Now this one I don't do anything. This and this two integration is independent. I will change here p to minus p. This is I am doing just for the to simplify the algebra. When I make p to minus p, what I will get? You see, I have a dqp integration, which I can write as dpx, dpy, dpz, right? My all going from minus infinity to plus infinity, right? Now I make a change of variable px to minus px, py to minus py, pz to minus pz. So if I do that, then for each px, py, pz, I will get a minus sign. So 3 minus sign will give you a resulting minus sign. And since I have made a change px to minus px, the integration limit will also get inverted, plus to minus. But I have again 3 plus to minus. Again, which I will reinvert them to minus infinity to plus infinity. Again, I will have 3 minus sign. 3 minus sign will give me 1 minus sign. And from there, 3 minus sign will give me another minus sign. So there will be no change in this integration. Ultimately, if I change the px to minus px, then for integration minus infinity to plus infinity, then my dqp will not change because of the 3 minus sign appearing there and 3 in the limits. So that 6 minus sign will give me nothing. So then pi x I can write as, this will not change sign. Remember, omega is a function of p square. So if I change p to minus p, nothing will change. Only ap will become minus ap, and that e to the minus p dot x will become plus p dot x. Now the advantage is that then e to the ipx, plus ip dot x and plus ip dx I can take common, and then my pi x becomes this. And then our pi x also, same trick I can do here, and pi x will become just e to the ip dot x I'll take common. Because I am doing this, I have to calculate the square of pi, square of pi, and if I use this trick, then the squaring will become easier. I'll have just like a plus a dagger, and then this I don't have to bother because it has come out as a common factor. Okay. So now this is my pi and pi. Now let us calculate the commutator pi x prime minus pi x prime phi x. This commutator, let me calculate. Like I had calculated the commutator xp for the harmonic oscillator. So what I do, I put this phi expression for phi, which I have shown you, and the expression for pi, which I should do only that since p is a dummy variable, here I should use d cube p, but when I am writing this, I should use d cube pi prime, right? So this is dummy variable, so I have done that. So product of pi into pi minus pi into pi. This I have done, and then what I have done is just straight multiplication. Straight multiply that. If you multiply that, you will get, this is the 2 integration remaining, and then if you multiply, you get this. This is the multiplication you need to evaluate, and if you evaluate that multiplication, this is the 8 terms you will get, and this 8 term you will be able to combine them in 4 commutators. Right? Now recall that this commutator pi commutator has to be a Dirac delta function. That is the condition, quantization condition, which we have put from the, so this commutator pi commutator has to be a Dirac delta function. That is the fundamental relations we have, commutation relations we have put analogous to the one which is done in quantum ordinary, I mean non-relativistic quantum mechanics. So this particular commutator pi x phi x, this pi x prime, that commutator has to be I d cube 3 Dirac delta function with argument x minus x prime, or if you take y, then x minus y, right? Now this commutator relation, this will be satisfied, and what you have here within the curly bracket here, in this 2 curly bracket, is the 4 commutator. Unless that 4 commutator satisfy these relations like AP dagger has to be 0, and AP dagger prime has to be this Dirac delta function. Except this AP dagger, all other commutator has to vanish. If this condition you put within this curly bracket, then you get back the the commutation relations for the pi and pi. So this is the commutation relations you have to. So pi and pi, they are now operators, right? Because we have putting commutation relations mean we have promoted this classical dynamical variable to the operators. Like we have promoted the classical dynamical variable x and p to the operator. Same thing we have done here, right? So then this commutator you can write in terms of the 4 this pi commutator in terms of the 4 commutator in terms of the annihilation and creation operators, and then you put this this a commutator, a dagger commutator equal to 0, and a dagger commutator in terms of the Dirac delta function. Then what you get back is the commutation relations which you started with. That means this is the commutation condition we put. That has imposed a kind of commutation relation between a and a prime, which has to be this, and this has to be 0. This is the commutation relations the annihilation and creation operator should satisfy. This is very important. Now I will show you that this kind of commutation relation actually also the beauty of the quantum field theory is that we are discussing the scalar field theory, right? Scalar field. Phi is a scalar field. Scalar means we call a field scalar when if I quantize that particle and get a quantize that field and get a particle which has spin 0, then it is a scalar field. So this is a scalar field. We have started with scalar field phi. When we are quantizing it, so it will give me a particle which has spin 0. That means it has to be bosons. And we'll see that these commutation relations automatically satisfy the statistics, both statistics which is required for the scalar particle. For fermions, we'll see that these will become anti-commutating relations, and they will also obey the Fermi-Dirac statistics and the Pauli exclusion principle will be automatically imposed. Okay, so these commutation relations are very important. Now we have calculated the L, the Lagrangian density. We have also calculated the Hamiltonian density, right? We have also calculated the Hamiltonian density. Now, this Hamiltonian density we have written in terms of pi and phi. I have shown you this. Now, this is the Hamiltonian density we have derived. Now, if I integrate this over d cube x, then I will get the total energy of the system. Right? So now d cube x 8, which is given by pi square. Yeah, so pi square. So I should just calculate pi square. Pi I know, so I just square it. But when I square it, again I should remember that I have an integration about d cube p, and pi x into pi x, there are 2 pi x, but then since p is a dummy variable, I am integrating over p. So once I should use d cube p, and other I should use d cube p prime. So just what I do, I take the square of this pi square with d cube p and d cube p prime integrations, right? Just I do that. Just square it, then you will get this. This algebra, if you do in detail, then you will see pi square x will be nothing but this d cube p 2 pi cube omega p by 2, and this annihilation and creation operators. Now in the Hamiltonian, you have another term which is you see this is gradient of pi square. Now pi I know in terms of annihilation and creation operator. I just take the gradient. If I take the gradient, that will give me just a p vector, right? And again pi square, pi I know in terms of annihilation and creation operator. The pi square will again I will be able to calculate. Calculate is very simple, and every step is done, and these notes will be available to you. So gradient of pi, if you do, as I said, there will be just a p square term coming here. Because if I take pi, which depends into the ip dot x, when I take a gradient, there will be p square appearing there. And then pi square will be this. Now I add all these terms with gradient pi square, gradient pi square, and pi square to get the total Hamiltonian H. This is really interesting, and you will see the H which you will get after all this is nothing but d cube p by 2 pi cube, right? D cube p by 2 pi cube, omega p, right? E dagger a plus half of this commutator. Now, you see this a dagger, and for the harmonic, single harmonic oscillator, what you got there? It was omega a dagger a plus half omega. Right? Because h bar is equal to 1, right? Now, this a dagger a is sometimes, it's called a number operators. So, omega into number operators, for harmonic oscillator, you got omega into number operators plus this half the 0 point energy, right? Now, you see what you got is the same. You got the number operators times the frequency omega, but here I have shown you that you have infinite number of oscillators. So, that is why you have a d cube p integration. You have to integrate over infinite number of the infinite number of harmonic oscillators. So a dagger a is nothing but n. So n omega, actually n h bar omega, but h bar is 1. So n omega is energy of a single harmonic oscillator, and then integration over, since I have infinite number of harmonic oscillator, I have to sum them, but p is a continuous variable, so I am integrating it. So that's the total Hamiltonian of the particle, right? Now of the system. Now in ordinary harmonic oscillator, you will have a half h bar omega, right? Now h bar is 1, so half omega you should have. But here what is happening, you see what is appearing here is AP dagger, right? Now what is AP dagger? You know the AP prime dagger satisfy these particular commutation relations. We have just derived it. Now AP dagger, if both are P, then it will be a Dirac delta function with argument 0, which will diverge, right? So what you have the Hamiltonian, where you have this, you know, energy part h bar omega into number operators plus a infinity. But that is not surprising, because if you have infinite number of harmonic oscillator and each of them has energy h bar omega by 2, then if the number is infinite, that will diverge. That is what has happened. So everything we can understand in terms of the harmonic oscillator, right? So that's nothing surprising, but it is disturbing. It is disturbing because infinity is hanging around here. But then I told you, let me make two comments here. One comment, number one, is normally we never measure the absolute value of the energy. We will measure the change in the energy between two states. So then if you have a common infinity, it will get cancelled. Number two, in the beginning I have shown you, for the ordinary harmonic oscillator, if I order the you know, variables properly, then the 0 point energy doesn't come. That is what is I have done there is normal ordering. I'm just making that comment here today. We'll discuss that in detail when we'll discuss the Weeks theorem. So though it is disturbing, but we can get rid of that. Don't worry. Okay. So this is what it is that you have the Hamiltonian for n number of oscillators, infinite number of oscillators, but this will become, of course, this will of course give you infinity because of that fact. Okay. Now, you know, this Hamiltonian, as in ordinary quantum mechanics, that Hamiltonian, if you take a commutator of that Hamiltonian with annihilation and creation operators, then they will satisfy this kind of commutation relations. This is also valid in your ordinary, quantum mechanics. Now let us define the vacuum. This is the free vacuum. Okay, because we have not put any interaction in the system so far. We are discussing free field case. Klein-Gordon equation is a equation for the free field. We have not introduced any interactions. So suppose I have a vacuum which is denoted by this 0 kth vector, and the annihilation operator operates on that, I should get 0 because there is nothing to annihilate, so it will be in the vacuum, so it will give me 0. So for all the P, this will be true for all the P, right? Now from there, so suppose I have this vacuum, I can operate a creation operator and create particles there. So I can operate on this vacuum AP dagger. I will create a particle with, or excitation, I will create excitations with momentum P. If I again operate Q dagger, I will be creating another excitations with momentum Q or the frequency omega Q. Right. So if I operate many of them, then that will be a state of the Hamiltonian with energy H equal to omega P plus omega Q and so on. Right. Okay. So this H, what we have got is omega P. This is very important. Please remember this only, that omega P times the number operator. Let us see. And that omega P we have defined as, and let us see now what is that P. Now let us calculate again, go back to the energy momentum tensor, which I have calculated when I discussed the Noether's theorem. This was the expression for energy momentum tensor, if you remember correctly. I take this 0, 0 component, mu equal to 0, nu equal to 0. Then this will be my case, and this is nothing but minus L plus pi dot. That is the Hamiltonian density of the system. Now, from the same Hamiltonian, energy momentum tensor theta mu nu, which we got from Noether's theorem, as I said, this mu can vary from 0, 1, 2, 3. So mu equal to 0 is the temporal component, 1, 2, 3 are the spatial component, and normally sometimes this 1, 2, 3 are denoted by I or JK, and this 0 to 3 is denoted by mu nu, these variables. Okay. Now let us calculate from that theta 0 I, mu equal to 0 and nu equal to I. So this is if I put mu equal to 0, nu equal to I in the expression, I get this. So delta I phi is the derivative with respect to spatial coordinate, like delta x, like x, y, z. This I can be 1, 2, 3 means x, y, z. Okay. So the theta 0 I is this. And this G0 I, this metric tensor is zero, right? Because this has only, this G mu metric tensor only has a non-zero diagonal component. All off diagonal components are 0. So this term vanishes. So theta 0 I is nothing but this, you see, del L del 0 phi is again phi dot. So del L del phi dot is pi, like dl del q dot. So this is pi, the conjugate momentum, and this is, you have del I phi. Now pi I know in terms, expanded in terms of the annihilation and creation operator. Phi I have expanded in terms of the annihilation and creation operator. So I can calculate phi is this and pi is this. I can calculate del I phi. If I do that, what will happen? Derivative with respect to the spatial components, and this pi will come here, pi, right? And then this pi I can calculate, pi I can put from here, del I phi put from here, and what I get, the momentum, total momentum will be d cube p by 2 pi cube pi ap dagger ap. So this is the number operators times the momentum, right? The momentum p. Now please see here, this h is nothing but omega times the number operator. Now what is omega? If you remember, omega was defined as root over p square plus m square. So what is that p? The p which appeared, please, this point is very important, which p which appeared in omega, right, is nothing but the momentum, right? So it is nothing but the momentum. So that p is nothing but the momentum. So omega p equal to p square plus m square. That means omega p square equal to p square plus m square, right? This is the Einstein energy momentum relation. See, if p is the momentum, which you have identified this particular way, and m square is the mass, then their square, sum of their square must be equal to energy, right? Now, because c we have taken 1. So this is the energy. So energy square equal to momentum square plus mass square. So then these excitations are what? They are simply the particles, right? So you see, the basic point now here is that we have started with the classical field phi, right? And then what we did, we have shown you that classical field phi satisfied the equation, Klein-Gordon equation. It satisfies Klein-Gordon equation, and that Klein-Gordon equation is nothing but a set of infinite number of harmonic oscillators, right? Now, when we quantize that, we got the energy, momentum, we got this Hamiltonian in terms of this omega. Now that omega, the p which is appearing in that omega is nothing but the momentum of the particle. Then what we are arguing, that p square plus m square, which is omega p square, which we have defined like the frequency, it is nothing but the energy. So when we quantize this scalar field, I have got particles. Because this particular relation is valid, Einstein relation, Einstein gave this for particles. So when I quantize this classical field, I got the particles. And similar thing will happen if you do with the Maxwell equations, which we did for the Klein-Gordon equations. Suppose you do the same thing for the Maxwell equations. If you take the Maxwell equations, right, and in the Maxwell equation, you have the scalar potential, electric and magnetic field. You know that electric and magnetic field I can substitute in the favor of scalar field phi and the vector field A. So now I have that phi and A again can form a 4 vector. And now if I use this and the solution of the Maxwell equations gives me the electromagnetic waves. Now if I take the Maxwell equation, and then if I can write down the Lagrangian for the Maxwell equations, and from that Lagrangian I will have the dynamical variables like phi and A, the scalar and the vector potentials, will by taking the derivative of the Lagrangian with respect to these time derivative of these dynamical variables, we'll get the conjugate momentum. And if we put a quantization of that conjugate momentum with the dynamical variable, I'll get a ultimately I'll get the concept of photon. Just simply concept of photon. What will happen there? I'll get omega p equal to the energy equal to p, because c equal to 1. And that's how you get the concept of photon, by quantizing the electromagnetic field. We'll discuss that later. But what we did here, we have quantized the classical fields and got the particles. So now these are particles, because by quantization, what we got, those excitations are satisfying the Einstein energy momentum relation. So they are simply the particles, right? And you can create them. Similarly, you can operate, on the vacuum, AP dagger, AQ dagger, all these creation operators, and create particles with momentum P plus Q and so on, right? And they will satisfy they are the momentum of the particle. So these excitations are nothing but particles. So omega now I can replace by energy E. So classical fields I have started with. I was saying that these are classical fields. Then I put the quantization relations, and then I got the particles as the excitations of this field. They have appeared as particles, and this is this with the interactions and all that. This will ultimately, the scalar particles may be the Higgs. Okay, with that, but that we are far away from that. We are just discussing the. Tell you one or two more interesting thing is that, we have what kind of commutation relations we have put. The commutation relation which we have put for the AP and AP dagger, you see, I have put a commutation relation. What is that? Probably I am far from. A dagger, AP dagger, AP prime dagger equal to 0. So AP dagger, AQ dagger equal to 0. If there are two dagger is equal to 0. That's what the commutation relation I have put. And what is the consequence of that? Let us see that. So by AP and AP dagger, AQ dagger, I can create particle excitations which we have identified with the particles, right? So this is the quantization of the fields which we have given you the particles. Now you are in the particle domain. Now with that particle, you can do the particle physics, all kinds of things you can do, but you have to, of course, put the interaction. Now, let us see the consequence of the commutation relations. Suppose you have a vacuum, I operate a Q dagger. I'll be creating a particle with momentum Q. AP dagger, I will be creating a particle with momentum P, right? Since AP dagger and AQ dagger commutes, this will be same as AQ dagger, AP dagger. So, in this state, I will have a moment particle in the order, let us say PQ. Here, I will be creating a particle in the order QP. But since they commute, they are same. So when I have interchanged these two particles P and Q, there is no change in any, there is no change. So that means that commutation relation enforcing the statistics for the bosons, which is Bose-Einstein statistics. That also tells you that Klein-Gordon equation actually describes the bosonic fields, and quantization of that leads to bosons. Of course, they are scalar. So by quantizing that, you have got a particle which is scalar. That means they have zero spin. So they should obey the Bose-Einstein statistics. If I'll interchange them, there should not be any change, and that is what we have got. That's it. I mean, you see, this is the so quantization. Within the quantization conditions, the statistics for the particles is built in. Okay, so this is I think this is a good point to stop here today. If you want, then I can just discuss there is some problem with the commutation relation, contravariant vector. I will discuss, or I can discuss that next day, but it is up to you. Can you hear me?
Yes. Yes, sir. You are audible.
Sorry. Yeah.
Yes, you are audible, sir.
Okay. So should I stop here, or that contravariant I'll mention a few words about that. And but if you have any question, you can ask.
Yes. From the participants. Yeah. From the participants.
Or should I just discuss that contravariant part?
Yeah.
Should I?
Sir, could you please explain one second? Causality, it's a violation of causalities. No, sir.
That I'll discuss. When I'll calculate the propagator, I have just indicated today is that, you know, that I have calculated the amplitude for the particle when it is propagating from a, you know, point from x0 to x. I have calculated the propagation amplitude, and you will see that that propagation amplitude is non-zero for any t and x. For any arbitrary t and x, it is non-zero. But the, you know, particle cannot propagate beyond the light cone, you know, because it has the maximum velocity of light, right? It cannot cross that. So, if the amplitude becomes non-zero for any arbitrary x and t, that will indicate that you are violating the causality. Something which has a that will happen if it's you have a velocity which is more than the velocity of light. Now the question is then something is propagating beyond the light cone. Now how to restore is that through this quantization which I have done today for the real scalar field. When you do this for the complex scalar field, what will happen? The propagation amplitude outside the light cone for the particle will be exactly cancelled by the propagation amplitude of the antiparticles. So the appearance of the antiparticles in quantum field theory restores the causality. That we have not discussed yet.
Okay, sir. Thank you. Any other question from the participants?
The participants who ask me for the contravariant and covariant vector, please, Professor Alam will give you that answer if you have any confusion of that. Yeah.
Should I share that?
Yeah.
Okay.
Yeah.
I can give a detail. I mean, mathematical. I can give it why it is called contravariant, covariant.
Okay.
Let me just give a feeling today. Maybe just that will help. But if you know the detailed mathematics, then I can give it tomorrow. But I have very quickly how to share it. Let me see. So there is no question. That means, is it a problem that is there any communication gap? Let me.
No, sir, it is okay.
Yeah. I don't think so. Yeah.
Sorry?
I don't think so.
I don't think so.
You know, going perfectly right. So we're trying to grasp your lecture, sir.
So one question is, one question is coming from the message. Yes. So from Dinesh Tarachandani, that why did we replace P with minus P?
No, that is just for mathematical convenience. If you don't do, there will be your mathematics will be little bit more complicated. You see, when I change that P to minus P, I could take e to the with the annihilation operator, I have e to the ip dot x, and with the creation operator, I had e to the minus ip dot x. So if I want to take e to the ip dot x common, then the exponential, in the exponential, I should have the same sign in both the exponential. So that is why in the second term I have just changed p to minus p. If you change that, then what happens? You get simply the algebra will become simple, nothing else. Should I go back there and tell you? Let me see if I can get back. I mean, there is no physics in that. There is no, one can do it without what I am doing. Sharing is, I don't know. Maybe I have gone out. So let me see. Stop sharing, and then let me again share. Okay. Present now. Window. Is it the one? So let me see. Where is that? Okay, I'm sorry, I'm unable to share. So let me see. Try. Where is that? Have I closed it by chance? Okay. Probably I have closed it by mistake. Let me go back there. Okay. So I'll explain to you why I have done this. It is optional. So let me see. Actually, this is sometimes I am unable to do it. Sometimes my daughter helps me. Okay, so let me just explain to you why I have done this. You see, Dinesh, it is like this. Where is that? One more thing is that my handwriting is very bad. Okay, so phi x is like this. You see, Dinesh, this phi x is d cube p 1 by 2 omega p a p to the I plus p dot x and u to the minus I p dot x. So my intention is, if I change here p to minus p, I'll be able to take this common, right? And if I can do that, then my algebraic manipulation will be simpler. So what I did then, I just changed this p to minus p here, right? And if I make that change, I have to then see whether I am in other, here I have made p to minus p. So then I have to see this will become e to the ip dot x, e to the plus ip dot x, and then I can take common. But then this ap should become minus ap, right? That is what minus you see, where is that? Minus ap minus p. And then I have to see, but I had another quantity like this d cube p by omega p. Now omega p, if I make p to minus p, will not change sign, because omega p is a function of p square. So minus sign will not change anything. Now in this d cube p, this is dpx, dpy, dpz, right? So px will, if I make px to minus px, py to minus py, pz to minus pz, there will be 3 minus sign. So ultimately I'll get 1 minus sign from there. And all the px, py, pz, the limit is from minus infinity to plus infinity. So if I change px to minus px, then the infinity will be, limit will become infinity to minus infinity. But there will be 3 of them. So another minus sign will come from there. So that minus sign and the other minus sign will get cancelled. So there will be no change in this. This will remain unchanged if I make p to minus p, right? And in this term, this will become plus and this will become just minus p. That's all. I'm changing p to minus p and again reverting it back, so that I can take that to common. And this is done, you see here, I have done very note. d cube p is minus infinity to plus infinity, all that. Then if you change all this px, py, pz, right? 1 minus sign, and then when I have inverted, this has become plus infinity to minus infinity thrice. That will give me another minus. So minus minus will get cancelled, and everything will remain same. d cube p will remain d cube p. And omega is anyway is a function of p square, so it will not change sign. So basic idea is to take this common so that my algebra becomes simple. There is no physics and behind it. And if you like, you need not take it. It just you can do without changing the sign also. Okay. Is it okay? Okay, thank you.
Yes. Yeah.
Any other question?
Yes,
Hello?
Jayanto. Yeah. Yes.
Yeah, I have a related question. I mean, the Lagrangian, which you have taken. I mean, suppose if that Lagrangian doesn't have a global gauge symmetry. In that case, I mean, if it becomes that it has a local gauge symmetry rather with respect to the spatial positions.
Good.
So how it will affect the canonical quantization?
That's right. So that's a very interesting and very profound question. So please note that where is my screen going? That is something. Where is my screen going? Can you see my screen?
Yes. Yes.
That is a very important question. Certainly, let me just tell you what will happen. So this is my Lagrangian, right? Can you see this?
Right.
Now, if I change phi by a factor e to the I alpha phi, right?
Right.
Now, if my alpha is a function of t and x, then there will be a del mu alpha terms coming here.
Correct.
Right?
Correct.
So I will have an extra derivative term with respect to del mu alpha.
Yes.
And why it is happening, you see, whenever you take a derivative of a function, you need to know the function at 2 points. Like when you calculate df dx, I need to know the function at f x plus h and f of x. Then I subtract them and take the limit h tends to 0 so that I get the derivative, right?
Correct.
Now, when I have a derivative, then what is involved is phi at 2 different points, right? So if I have a local gauge transformation, then that means if alpha is a function of x, then I'll have 2 different alpha, right? Right. Now, and that will give rise to a derivative of the alpha function, del mu alpha kind of thing. So, but in this Lagrangian, I don't want that term, right? So what then I will do is that is actually asking you that you to cancel that alpha, you have to introduce some interaction in the system. And that interaction term should also transform in such a way that you will have the interaction, that interaction term will cancel this alpha. You know, what I am saying here is that when you have a local gauge transformation, then to make the Lagrangian invariant under the local gauge transformation, you have to introduce the interaction.
Oh, I mean the free Hamilton. I cannot write the free Hamiltonian.
Absolutely.
Yes.
Absolutely.
So any kind of local gauge transformation or local gauge symmetry means there is a kind of interaction.
You have to introduce interaction, otherwise your Lagrangian will not remain invariant. So the del mu alpha terms which will come from this kind of derivative, the other del mu kind of alpha terms should come from the interaction term. This is the free term.
Correct.
And the other del mu alpha term should come from the interaction term, and they will cancel each other.
Thank you. Perfectly understood. Thank you.
And I'll give an example. Let us consider, suppose you consider the Schrodinger equation and in an electromagnetic field, right?
Yes.
Write down the Schrodinger equation in the electromagnetic field, then you know the vector potential A, right, will appear in the Schrodinger equations because I have written down that in a magnetic field. Now, that vector potential Maxwell equations allows me to change that A to A plus some gradient of chi.
Yes.
Right? That base freedom I have.
Yes.
So if now in the Schrodinger equation I have A. Now I suppose you put you change that A to A plus grad phi, then my Schrodinger equation is changed.
Yes.
Now, but through the gauge transformation, my physics should not change.
Correct.
Then what I should do? The Schrodinger psi, I should give a local phase transformation.
Yes.
The local phase then from Schrodinger term, that local phase transformation will bring a derivative and cancel this delta chi.
Yes.
Okay. That I discuss when I so what perfectly this way I will actually introduce the interaction that I have the free Lagrangian. I'll give a local gauge transformation. Then when giving local gauge transformation, I'll show you that I am in difficulties because a del mu alpha term is hanging around. To cancel that, I'll put an interaction. And when in the interaction, I'll put the same gauge phase transformation, I'll see that two are just cancelling each other.
And the interaction that is necessary to preserve the local gauge symmetry, I mean, that will define that how the perturbation series will act, right?
No, once I put the interaction, then from the interactions I have to develop the perturbation theory. Feynman diagrams and perturbation will come from there. So the interaction will come through the local gauge transformation.
Okay, thank you.
Okay. That is precisely how you will get the Lagrangian for scalar, complex scalar field, and that is precisely will give you Lagrangian, which will describe Landau-Ginzburg Higgs mechanism and all that, and even Anderson Higgs mechanism and all that. That I'll show you if time comes that how that can help you to understand the Meissner effect even in the superconductivity.
Oh.
Okay.
Professor Alam, another question coming from Mahmudul Hassan.
Please,
yeah. Is the method of relativistic canonical quantization applicable to non-linear field?
Sorry?
Is the method of relativistic canonical quantization applicable to non-linear field?
See, so far what we have discussed is the free part of the Lagrangian, right? It is the free part, and in the free Lagrangian, Euler-Lagrange equations is always linear. This non-linear interaction term will introduce, like here we have stopped at a term phi square, phi cube, phi 4 term will introduce, and we will see how the theory will develop. Just wait for 1 or 2 days more.
Okay.
But whatever I have discussed, let me know whether it is understandable to you or I should change whatever.
Yeah.
That is important.
Okay.
That I'll come.
Okay. So, any other questions from the audience? So I think no questions left.
Okay. So am I going fast? Is it understandable? Please, some student should tell me.
Yeah. So students, Aditi.
Am I going fast or slow or what? And
Aditi Ghosh, respond.
You teach a lot, so you can also guide me whether I am fast or slow or what.
So we are beginner to relativistic quantum fields, so we are trying to observe the essence as much as possible. It's quite understandable. I think it will be quite beneficial for us if we get the PDF of the stuff we are providing.
Right. So PDF for the first 2 lecture I have already sent. Today's one I will send tomorrow or day after. First 2 lecture I have already sent.
Those who are interested, please send us the email. So if we get the email ID, then we can send the notes. So it is necessary to get the email ID.
Okay, so I'll mail you tonight.
Yeah. No problem. Okay. So, another from Rajesh Shankar Bordoloi. Oh, I see.
Yeah. Yes, please.
Yeah. No. He put his comment that your face is perfect, at least for me. Okay. You can see the chat, please, Professor Alam.
Oh, what is that?
Yeah.
As I said, I am learning this from my daughter.
Yeah. They are more tech savvy than us.
Oh my God.
Raising hand.
Oh, Dr. Ritapurtha raised his hands. Okay. So
Hello. Yes, I have one question. Why are we putting a dummy index when we're integrating momentum twice, like P and P dash? What it does this help with the calculation?
No,
Integration?
you have to do that. You have to do that. You see, so suppose you have a term which is phi x square. So phi x into phi x. So for one phi x, if you integrate over delta p, then for other phi x you have to integrate, do the integration over p prime, isn't it? Otherwise it will not be, your result will not be coming correctly. I have to have. Acha, somebody is asking something here. Okay, maybe I will explicitly show you. If you don't do that, what is the problem we'll face?
Yes. If you could show that, yes.
So next day, what I am going to do, first I'll give you some clarification about the contravariant and covariant part, and then I'll and this part, and then I'll go to the lecture.
Sir, I have one question.
Oh, Rajkumar.
Rajkumar. Yes, sir.
Bolo, কি আছে তোমার?
Sir, by the principle of least action, we have derived the Euler-Lagrange equation, that is del L by del phi minus del mu, del L by del mu phi.
All right.
And we can take the momentum conjugate of phi is
Pi. That is pi, right?
Sir, can you hear me?
No, it was disconnected in the middle.
Can you hear me, sir?
Now I can hear you. Please repeat.
Yeah. Actually, we have the Lagrangian Euler-Lagrange equation del L by del phi minus del mu del L by del phi. But when we take the momentum conjugate of phi, we have taken del L by del phi dot, not del mu phi. It is understandable, my question, sir?
Not clearly, but that is the analogy. When I mentioned when I am doing this, always I am keeping an analogy with your classical mechanics. So please try to see it. If you have still some confusion, I'll let you ask me next day. Okay? Actually, probably you are trying to be on Rajkumar, na?
Yes, sir. Actually, the difference is we have taken phi dot.
Rajkumar.
Yes, sir.
কেটে যাচ্ছে তোমার ভয়েসটা আমার কাছে কিরকম?
Now it is okay.
ওকে হচ্ছে, তারপরে আবার sometimes it is going
actually when we taken the
you can do one thing, you can give me a call.
Yes, sir. ठीक है.
Okay, better.
Okay.
So, any more question?
Any questions? I think no questions left now. Yeah.
Okay, thank you.
Okay. Thanks again, Professor Alam. So we'll meet tomorrow at 7:30.
Yeah, sure.
Okay.
Sure.
Thank you very much.
Good night, sir. Thank you.
Good night.
মাসুম আর মুর্শিদ, বলছিলাম হ্যাঁ ওই যে রিকোয়েস্ট মেল আইডি গুলো আসছে, হ্যাঁ রিকোয়েস্ট মেল আইডি গুলো একটুখানি তুমি সেভ করো, হ্যাঁ সেভ করে নিয়ে ওদেরকে ওই এগুলো পাঠিয়ে দাও। হ্যাঁ অথবা এই যে চ্যাট যেটা আছে এটাকে কপি করা যাচ্ছে না, চ্যাটটাকে তাহলে সুবিধা হবে তোমাদের মেল আইডি গুলো তাহলে পেতে। এখান থেকে আমি কপি করে নিচ্ছি, একসঙ্গে পুট করে দেবো। হ্যাঁ কারণ এই মেল আইডি গুলো তুমি একটা মেল বক্সে রেখে দেবে, তাহলে সুবিধা হবে ফার্দার নোট গুলো পাঠানোর জন্য আর কি। হ্যাঁ আর এখন আমি একটা ই করে দিচ্ছি স্যার। and the recorded videos I want to inform the participants that the recorded videos are now in YouTube also, which we have mentioned earlier. So one by one, we will put the recorded here. YouTube. Okay.
Okay,
We can leave. Huh?
Okay, ঠিক আছে।
Okay, sir. এটা আপলোড করো।
নীলুফার, এই মাইক্রো এটা রেকর্ডিংটা অফ করে দাও এবার।